So engineers and scientists have projects that they do that require a certain amount of energy. And the amount of energy they need for their project will be determined by the amount of work that must be accomplished for that task. So work is defined to be the force exerted times the distance that that force has to be exerted across. So it's a fairly easy computation. So I'll give you an example. I have a bucket here that has 200 pounds in it, and I'm going to lift it. So what did I just do? I lifted 200 pounds 6 feet. So there's two things you just discovered. One, I'm a lot stronger and taller than I look on the videos. Secondly, I just did a certain amount of work. I took 200 pounds and lifted it 6 feet. So the calculation for work is just force times distance. So I did 1,200, and what would the units be called? Since you're multiplying, they'd be called foot-pounds. So this is a unit of weight or force, and this is a unit of distance. And we want to use force and not mass, because there's going to be a different amount of work for lifting that bucket on Earth than there would be on the moon. So we're going to use pounds in the US system, and if we use the metric system, we're going to use newtons, not kilograms. Anyway, that seems really easy. Why do we have to have calculus involved? Well, as you might have kind of guessed, sometimes the force you're exerting isn't the same throughout the whole distance you're exerting that force. You have a variable force rather than a constant force. So you actually have a function that tells you how much force you have depending on the position you're exerting that force at. So this could be in pounds, and this could be in feet. So you might have a force, instead of being constant, that looks something like that. And say you're exerting it from position A to position B. Well, what we have to do, and again, as you may have guessed, is we're going to break this distance from A to B up into n different smaller distances. And we're going to call this x sub 0 and x sub n, and we're going to pick a section from x sub k minus 1 to x sub k, the kth section, and then we'll randomly pick out a value in there called c sub k. And if I go up to right there, that straight line, that vertical line, is representing the force at that position. So if I multiply that times the change in position, the area of this rectangle is going to give you the amount of work I did in this little bit of time period. So what it's going to be is f of c sub k times the change in position, which is delta x sub k. But I've got n of these changes in position, so I'm going to sum them up from k equals 1 to n. But since that force wasn't the same this whole time, and there's going to be a little error, we take the limit as n approaches infinity. That way, we're taking an infinite number of forces times really, really, really small changes in position or distances. And what do we find? We have an infinite Riemann sum, exactly in the form we've defined it. So this is just a definite integral. And that's exactly the formula we have to find work. You're finding that what integrals do is they multiply. They multiply two things. They multiply these units times these units. And so you get what? You get foot-pounds. It just does an infinite number of these calculations. So now that we've got a formula, let's try a few problems. So a 50-pound bucket, so that's how much the bucket weighs just by itself, has 100 pounds of water initially. But as you start to lift the bucket, a hole develops and continues to get larger as you lift, so that the weight of water is 100 minus 4x squared pounds by the time it's lifted x feet. And they want to know how much work would it be required to lift it 8 feet. So this is a little bit harder than me just lifting that bucket because the force is changing. So the force, the weight is 100 pounds plus 50 pounds initially. But then you have to subtract 4x squared, because when it's 1 foot up in the air, the weight of the water is only going to be 100 minus 4, or 96. And you can see as x gets bigger, the weight is getting less at a faster rate. Anyway, this is my f of x, and then I just have to multiply that by dx, and then you go from where? From x equals 0, and it would be until x equals 8. But you have to be careful, because what do you see? Before you get to 8 feet, it's run out of water, so you don't want to keep trying to reduce the weight of the water once it gets down to 0. So when is this going to be 0? When x is equal to 5. So when the bucket gets to 5 foot, then you don't want to try to reduce the water anymore. So you just go from 0 to 5, and then you don't need calculus to do those last 3 feet. You'll just have a 50-pound bucket, and you're lifting it 3 more feet. So I hope you understand that this is going to give us the total amount of work. So 150x minus 4x cubed over 3 from 0 to 5 plus 150 to lift the bucket that last 3 feet. So you get 750 minus 4/3 times 125 I think that's right, plus 150. So you get 733 and 1/3 foot-pounds. And that's the total amount of work that was required. So, trying to give you one that might even seem more important to you, like when we send rockets up in the air, what if we just had a model rocket and the engine burns 5 ounces of fuel in lifting your model rocket 200 feet? Well, the work to get the rocket up is pretty much just like lifting a regular bucket up. It's not going to require calculus. It's just the distance times the weight of the rocket. But the fuel itself is, as the rocket is going up, the fuel is burning. So the amount of fuel is decreasing. So that's where we require calculus. So it wants to find out how much work was done just to lift the fuel. So what we have to do is get a force. We know the answer is going to be f of x dx, the force times the distance, and it's over 200 feet. So you could call ground position 0, and then x equals 200 when it gets to its highest point. So we want to go from 0 to 200. Now, probably the trickiest part about this one is figuring out what the force is. Well, it starts out at 5 ounces, but then it's going to be reduced at a constant rate. So what is that rate? Well, it loses 5 ounces in a period of 200 feet, or 1/40th ounce per foot. So if you subtract 1/40th ounce per feet times the number of feet, that should give you how much fuel was burned up by that time. So let's see if this works. When x is 0, you have 5. When x gets to be 200, you have 5 minus 5, or 0. So that seems to work. So when we go to do the fundamental theorem, we get 5x minus 1/40th x squared over 2 from 0 to 200. So 1,000 minus 200 times 200 over 80. A little cancellation, and you get 500. So 1,000 minus 500 is 500, and again, this time, it's not foot pounds, it's foot ounces. So if you really needed to convert it into foot pounds, you would just divide by 16, and then I think it's 31 1/4 foot-pounds of work just to lift that rocket ship. So these are types of decisions that have to be made to know how big of an engine you need to lift a rocket up into the air, whether it be a model rocket or a large rocket. Okay, so let's look at a different type of work that's required in the real world. Many engineering feats require springs in them, and some springs are really big, and it takes quite a bit of work to either stretch the spring out or to compress it. So, and now we're going to get into the metric system a little bit, where instead of using feet, we're going to use meters. Instead of using pounds, we're going to use newtons. So, I think you can see one of the biggest problems is finding out what the force is going to be. Well, there's one thing about a spring, and this was a physicist from England by the name of Hooke came up with a law that says for springs that the force is directly proportional to the distance that the spring is stretched or compressed, it doesn't matter, from its normal length. So if this is the normal length, the force is directly proportional to how far you've stretched it. So how do you say that? Kx. So the bigger, where x is the distance from normal, from its normal length. So you can see the bigger x gets, the bigger the force gets. And that would be true for a small spring or a really large spring. It's just that a larger spring would require more force, so it would have a bigger proportionality constant. So anyway, that's the good part about springs, is that you can always get the force just from Hooke's law. Now, sometimes you'll be given K and sometimes you won't be given K. In this problem, I didn't give you that. But I did say it takes this amount of work, 60 Newton meters, to stretch a 4-meter spring from 6 meters to 8 meters. Well, we have to know that work is equal to K times X. So, the force is equal to K times X, so the work is equal to F of X dx. So the work for a spring is always going to be the force times the distance, where the force is K times X. Now, where is this going from? 6 meters to 8 meters. But what's important is, how far was it from its normal? Well, its normal is 4. So 6 is 2 more than the normal. And 8 is 4 more than the normal. So that would be how much work it would take to make it go from 6 meters to 8 meters. And we know that that answer is equal to 60. So from this, we should be able to figure out what the proportionality constant is. So what's the antiderivative of kx? Kx squared over 2. And then we plug in, I can even bring this k right out front, so I get 16 over 2 is 8, minus 4 over 2 is 2. I get that 6k equals 60, so k must be 10. It would be 10 newtons per meter. That's the proportionality constant. So now we can find the work to do anything, because we know the force equation now is not kx, it's 10x. So if I take that force times the distance, it's going to give me the amount of work. Well, I want it to do 3 more meters. How much work is it going to take to do 3 more meters? Well, you're already at 8. So you're already at 4 from its normal, and you want to go 3 more, so you want to go to 7. So you're going to just take the antiderivative of 10x, 5x squared, from 4 to 7. So you get 49 minus 16, or 5 times 33, or 165. And it's going to be Newton meters. That's the amount of work to do that. So we've gone from the work to move rocket ships up in the air, to compress or stretch springs in some mechanical device. And now we're going to go to another type of work. So say you have a right circular cylinder container of height 4 foot and radius 3 feet, and it's half full of root beer floats. And what we want to do is we want to drink that root beer float. It's going to require us some work, and we have to decide, is that work worth it? So here's our container. We've got a straw in it. What do we know? The radius is 3 and the height is 4, and it's half full of root beer floats. And we know we have to lift it 1 foot above the top of the container because of the straw. So you have another 1 foot right here. So what can we say? We can say the work equals the force times the distance, just like it has always been. But the trouble is, the amount of root beer float, the force is fairly consistent, but the distance that you move it is different. The top amount of root beer float here, you have to move a different distance than the bottom part. You have to work harder for that bottom part. So what I'm going to do is just take a slice So I'm just going to take a slice of the root beer float right out of here. And I'm going to call the distance up from the bottom, you can call it whatever you want, I'm just going to call it x. And then, what's the distance across here? That's going to be, or what I need to do is find the force of this slice right here. So the force is going to have to do with the volume of that slice. Well, if you think about it, that little slice is just a really skinny cylinder. So it's going to be pi times the radius, which is 3, squared, times the height. Well, if we call this distance x, we could call this little distance right up here dx. So that's the volume, but to actually get a force or a weight, we have to take that volume and multiply by the density. So if I multiply this by 60, now I've got a force, because it's taking the number of cubic feet and multiplying by pounds per cubic feet, which means that this is going to be in pounds. Now, how far do I have to move this? Well, I have to move it from where it is up to here. Well, we know that this is x, and this is 4, and this is 1. So the distance you have to move it is 5 minus x. So if I take this number, which I might as well write 9 times 60, or 540 pi, and multiply it by the distance, which is 5 minus x, and then we have the dx. So if I multiply the force times the distance, that's what I get, and I have to add them up from where? Well, x is going from 0 to 2, because it's only half full. So if I do that calculation, I should get how much work it's going to require to suck that out of, all that root beer float out of the container. So what can I do? I can bring this big 540 pi out front, and then I can just take the antiderivative of 5 minus x, which is 5x minus x squared over 2. So you get 10 minus 2, or 8. So you get 4,320 foot-pounds of work to drink that root beer float. And if you're like me, you'd say it's definitely worth the effort if you really like root beer floats. Now, I'm going to try to do one that's analogous to this, but it's a little bit harder, and it's more like you would actually have in the real world, especially if you were a chemical engineer. And chemical engineers often have tanks that they have to move some type of oil or gas from one tank to another tank, or from a tank to some type of refinery. So here's a typical one. I have to admit that most tanks aren't spherical, but it's more fun. It makes it a little bit harder. Cylindrical tanks are much easier because the radius is always the same. So I'm trying to give you a little bit tougher one. So say you have a spherical tank of radius 8 feet, and it's half full of oil, and it tells you what the density is of oil. It's less than the density of root beer floats. which is probably good because then the oil floats on the top. So if you spilled some oil into your root beer float, you could at least suck the bottom part out and the oil would stay up on top. So anyway, you've got the oil in here and you want to pump it just out of the top of the tank. In this case, we don't have to go a foot above. So what we still want to do is the same idea though. Take a slice and let this distance, I'm going to let it be y this time because it's an up and down, because this time the radius is changing. So I'm going to let that be x. So x is the radius of this little slice. Y is the distance the slice is up from the bottom, and we'll call this little distance right here dy. I think you can see that I'm not actually going through and dividing this all up into delta y sub 0, delta y sub k. It always ends up to be dy in our definite integral. So, what is the volume of this little slice right here? The volume is pi times the radius squared times the height, which is dy. And then to make it into a force or a weight, I have to multiply it by the density. And now I'm going to have to multiply that times how far I have to move it. Well, I have to move it from here to here. Well, this distance is y, and the radius is 8, so this total diameter is 16. So the distance you have to move it is 16 minus y. And that's the work to move just that one slice. And then what do we have to do with our integral? Integrals are just going to add up all those really small slices. From where to where does y go from? It starts at 0, and it's only half full, so we only have to go to y getting to be 8. Now, you probably see a problem here. dy, so y is my independent variable, but I've also got this other variable in there this time. This is why this is harder than if it was a cylindrical tank. So I need a relationship between y and x. So if I draw in a radius right there of 8, and then that little distance right here is going to be 8 minus y. So now I've got Pythagorean's theorem going on. I can say x squared plus 8 minus y squared has to equal 8 times 8, or 64. If I just square this out, I have a 64 on both sides, so I'm left with just x squared equals 16y minus y squared. And look at it, I've got x squared here, so there's no need to solve for x squared. I mean for x, I can just leave in the x squared. And I can bring the 50 pi out front, so I just go x squared times 16 minus y dy. And that still requires quite a bit of calculation. I don't think it's worth your time to do that. It turns out to be approximately 590,000 foot-pounds of work. So it takes a lot of work. So you do need a fairly big pump to pump that out. And a chemical engineer would have to determine how big of a pump they needed, because pumps are rated in how much work they do per hour. So they could figure out from that how big of a pump would be required. Now, instead of doing the calculation, I'm just going to go really quickly and tell you what would happen differently if that tank was full instead of half full? Think about it a second. Wouldn't the only difference be instead of 0 to 8, you'd go 0 to 16? You just have to add up more slices. And what if you had to pump it 7 feet above the top of the tank to get it to some place where you could deliver it to? That would just mean what? Instead of 16 minus y, you'd have to add 7 to that 16 because it would be a farther distance that you had to pump it. So you just make that 23 minus y, and that would take care of that. So it's not like you'd have to redo the whole problem. So I'm hoping in today's talk you can see how valuable integrals are in solving scientists' and engineers' problems that they have to figure out in their jobs. So good. Have a good rest of your day, and I hope to see you the next time.